All right, so last time we talked for the first time about the constant acceleration equations. Most of the time in class today, we're going to spend using the constant acceleration equations for free fall and projectile motion problems. I want to start by just going through number 6. It asks you to draw a position versus time graph for what's going on. So I just want to walk through the thought process of that. It's pretty related to what we're doing in lab this week. So half of you have seen this kind of stuff more than the other half. But let's just sort of go through it. Okay, so a ball rolls down an incline. There is a figure on the problem, but I cut it off here. When it reaches the point A, it has a speed of 2 miles per hour. And when it reaches the point B, it has a speed of 4 miles per hour. Let me just calculate that real quick. I'm just going to do the conversion. So when it passes point A, oh no, I went the wrong way. When it passes point A, it's going 0.89 meters per second. And when it passes point B, it's going 1.79 meters per second. And it takes 3 seconds to get from A to B. And so for the first part, I'm just going to go through, let's see. I'm just going to go through part B, I guess. Well, maybe I'll, let's see how it goes after this one. So for part B, it says choose the 0 to be at the point A, and then choose the positive direction to be down the ramp. So positive is this way. And that means negative is this way. For B, we're just going to draw a position versus time graph of what's going on. And then for C, we're going to calculate what the position is at that point B. Okay, so a position versus time graph. What do you know about that? Since A is the point we're choosing is at 0, and the positive goes towards the point B, we know that this is going to be, the point A is going to be on that horizontal axis somewhere. Sorry, it's going to be on the vertical axis somewhere because that's our position. And the point B is going to be some positive number greater than 0. We know that because of the direction of the positive. Okay, are you with me on that? And so B is going to be somewhere here. And we know that it's going to get to B in 3 seconds. So it's going to look something like this. But then what about the shape of the curve between these two things? Well, what do we know about, so we know that at time equals 0, it's at this location here, at position 0. What do we know about the velocities at time equals 0 and time equals 3 seconds? At time equals 0, we know that it has a positive velocity that's, half of the positive velocity it's going to have at this point. So I'm going to just draw sort of a guideline representing the slope. Remember, the velocity is indicated by the slope on the position versus time graph. So I'm going to call that the slope at time equals 0. And the slope is going to be twice as big at time 3 seconds, so I'll call it that. I don't know. I mean, I'm not calculating that, I'm just sketching it. And now let's think about what we know about the concavity of this. Remember, acceleration is given by the concavity. So acceleration, if the acceleration is positive, it's going to be concave up. And if acceleration is negative, it's going to be concave down. Is this ball speeding up or slowing down?
Speeding up.
Speeding up. Over the whole thing, the velocity is positive, right? So if it's speeding up, remember the rule, if it's speeding up, velocity and acceleration have to have the same sign. So acceleration also needs to be positive here, okay? And so for a positive acceleration, we need this to be shaped like part of a cup. So I'm going to start out with the slope here, and then I'm going to make it concave up. Until we get to that other point and the slope is going to follow that other guideline. So that's how we know the direction that it curves. That's how we know it isn't curved the other way. Anytime there's an acceleration of any kind, it has to be curving. So then you know you have to figure out, is it concave up or concave down? Okay, what about calculating the position at B? We don't know yet what this numerical value is. I guess I'll calculate that and then we'll put it in the graph. So the first thing we have to do is choose our 0 position, positive direction, and then our 2 stopwatch instants, when we turn it on and when we turn it off. This shows the 0 position and the positive direction. Then time equals 0 when we click the stopwatch on is going to be when it passes the point A. And when we turn the stopwatch off to look at the number, that's going to be when it passes B. So now we've made all 4 of those choices. And now I'm just going to list out the possible variables, and then we're going to figure out which ones we know and which ones we want. Okay, when we click the stopwatch off, when the ball reaches the point B, do we know what it's going to say? What is it? Yep, 3. So time final is 3 seconds. Do we know what the acceleration is? No, we're not asking for that though, so we'll leave that blank for now. PI, do we know what the position is when we turn the stopwatch on?
0.
Right, so PI is 0. Do we know what the position is when it reaches B? When we turn it off? No, and that's what we're trying to find. Do we know what the velocity is when the ball passes A? We do. We're given the speed, so now we have to, on our own, combine that with the direction. So we know that the absolute value, I'll write it like this, we know that it's equal to 0.89 meters per second, but now we have to think about the sign. So is this object at this instant moving in the positive or negative direction?
Positive.
Positive. And then for V final, when it passes B, we're going to have to think of it the same way. It's plus or minus 1.79. And is that one moving in the positive or negative direction?
Positive.
Positive. So, okay, here's what we have. And now we want to look through the 3, constant acceleration equations and figure out if there's one that has PF in it and everything else in it is known. And there's only one variable that appears in all three of those constant acceleration equations. That's A. And we don't have A, and we're not trying to find it. So we know, thinking about it that way, none of those equations are going to work. If you want, you could just check them one by one and you'd see the same thing. So no equation works. So that's disappointing, you know? And so you can take a second to, you know, think about that. That's you. But then eventually you're going to be like, okay, I gotta move on with my life. So the next thing you want to do is figure out an intermediate variable that you can use to kind of piggyback your way towards getting the answer you want. And those piggyback variables are always either TF or acceleration. Okay, we already know TF, so in this case, we're just going to bank on the fact that we want to calculate the acceleration. Okay, so now we're going to look for an equation that will let us solve for the acceleration. And it looks like the simplest one of these three is going to work. It has acceleration in it. V final is known. V initial is known. And TF is known. So this is going to work. So 1.79 is equal to 0.89 plus A times TF is 3, so I'll write this as 3A. And now do the algebra. We get 0. Okay, I'm kind of messing around with the units here, but we have something like this. Okay. And so A is equal to 0.30, if you round it, meters per second squared. Yes?
As far as like format wise, do you want us to write out like basically everything that you were putting on that paper? Like unknowns, and then
I think it would be a good idea for yourself, but if you want to go just straight to the equation, that's fine with me too.
And
so
algebra wise, would you like to see that like first equation on there, or can we just start by plugging in the numbers?
You can just plug in the numbers, sure. Yep, I can tell what equation you're using. I'm just trying to be clear for the people. Like, I know a lot of people aren't really doing this stuff in their heads yet, you know, so so I'm just trying to make it so when you look at your notes, you can tell what's going on. Any other questions? Okay, so now we have the acceleration. And so what I'm going to do now is just, this acceleration is now another thing that we know. And so now we have more options for what equations we can use. So now let's think about what equation we can use to calculate PF, now that we know these and we know A. And it looks like the equation that will work is PF is equal to PI plus VI TF plus 1/2 A TF squared. So let's just check to make sure. We're trying to calculate PF, and that's in the equation. And then we know PI, we know VI, we know TF, and now we know A. So this one will work. So PF is equal to 0 plus 0.7989, wasn't it? Times 3 plus 1/2 times 0.30 times 3 squared. And you get that PF is equal to about 4.02 meters. And so now that we've calculated this, we could go back and label this point B as 4.02 meters. Yes?
How are you keeping track of the meters and seconds and like what our final answer is going to be? Because
Oh, what units it's going to
what
be?
unit?
Yeah. Okay, so what I'm doing is I know what, so I'm doing everything in SI units. So I know everything's going to be in SI units. And then I just know that if everything works out right, any answer for position is going to be in meters. And so I'm not doing any calculations with the units. I'm just plugging in the units I expect at the end.
Okay.
There is a more careful way to do it. It's just tedious, and I'm not expecting you to do it this way. But if you put the units in your calculation, they'll come out and tell you the right units. So you could go through and say PF is equal to 0 meters plus 0.89 meters per second times 3 seconds plus 1/2 times 0.30 meters per second squared times 3.0 seconds squared. And we can write that as 0.89 meters divided by seconds times 3 seconds. And then we can add that to 1/2 times 0.3 meters per seconds times seconds times 3.0 seconds. And then we're squaring that, so multiply it to 3.0 seconds again. And these seconds cancel with these cancel with these cancel with these. And now we're just adding two things that have units of meters. And so that really is if you have the time and the patience to do it, like that's a helpful thing to do, because sometimes you can catch your mistakes in what you're multiplying or whatever because your units don't come out right. But I kind of don't think it's worth the extra time investment. So this is like, by the way, you could do this.
Could you keep the initial units and then do the equations and just convert at the end?
Oh, yes, you could do that. On tests and stuff, I'm pretty much, I guess on the first test, maybe I'll make you do some unit conversion just because that's one of the topics that we've covered. But after that, I'm pretty much just going to give you stuff in SI units. So unit conversion isn't going to be like a big issue in this class. Any other questions about that one? Okay, while we're on this one, let me show you one more thing with this, because in the example problems that I've done and that I'm going to be doing, mostly I'm not going to show you what would happen if you chose different zero positions and positive directions. But let me just do it once so you can see how it works and how the different answers kind of tell the same story. So I think maybe this is something that it asks you to do in the later parts of this problem. So now let's say we choose our zero position at B and our positive direction up the ramp. Does it ask you to do this in this question?
Yeah.
Okay. All right, well, I'm going to draw, what do I have here? Well, I'm going to take the same stuff I had before. So this is all the stuff that we don't change. The ball does what it does. It doesn't know whether you're measuring it or not, you know? And so this stuff doesn't change, but what does change is where we put our stickers that declare this is our 0 position and this is what we're calling positive and what we're calling negative. So now this is the 0 and the positive is this way and the negative is this way. Okay. And so I'm going to draw a position versus time graph again. We still just have 1, 2, 3 seconds. It still is passing A at time equals 0, and it still is passing B at time equals 3 seconds. And if the positive direction is up the ramp and the negative is down the ramp, this 0.89, this should be meters per second, this 0.89 meters per second, is that in the positive or negative direction?
Negative.
Yeah, that's negative. So that slope is going to be, well, let me get to that in a second. We know that we're going to be at position 0 at 3 seconds, right? When we're at A, is that position going to be positive or negative? Positive, because if you start at 0 and go in the positive direction, you're going to be at something positive. So this is going to be A. And now I'm going to use what you just told me. We know that the velocity when it passes point A is negative. So I'm going to just sketch like a little guide slope. And when it passes B, is that velocity going to be positive or negative? Negative still, and it's going to be twice as great a slope. So I'll do that. And is it speeding up or slowing down? It's speeding up, and speeding up means velocity and acceleration have to have the same sign. So in this case, acceleration has to be negative, concave down, and so it's going to look something like, it's going to start out along that and do that. Okay. I'm going to choose to do this calculation. Time equals 0. I'm going to choose when it passes A. Time final is going to be when it passes B. We're going to list out what we know and what we want. Okay, we know that time final is 3 seconds. We don't know acceleration. P initial, we don't know. But if we're trying to figure out how far apart these things are, that's what we're trying to find now, what that P initial is. P final is 0. V initial, okay, V initial is plus or minus 0.89 meters per second. You already told me that it's moving in the negative direction, and so this time that's the velocity. And then V final we're given, that's plus or minus 1.79. You already told me that's in the negative direction. So that. And now the steps are pretty much the same. We have to calculate the acceleration first. What we're going to get is, so blah, blah, blah. We'll get that the acceleration is equal to, this time, negative 0.3. Okay. But notice that if you drew an arrow in the direction of the acceleration, it would be in the same direction. That arrow would be in the same direction that it was in the problem we just did, because negative now means what positive used to mean. Okay, and then now that you have that, you can use this equation. PF is equal to PI plus VI TF plus 1/2 A TF squared. And that tells us that this time you would solve for PI, and PI is equal to, what was it, 4.02? So some things look different, some signs change and whatever, but when it comes down to calculating how far those points are from each other, you get the exact same answer. All right, so now we're going to use the constant acceleration equations for the most important class of constant acceleration problems. So we're going to apply the constant acceleration equations to free fall and projectile motion. And the first thing I have to tell you is something that messes with most people's minds who haven't heard this stuff before. And that is, so I think most people grow up with kind of this idea that heavier things, gravity makes heavier things fall faster, okay? And you can think of some examples that give you that idea. If you go to the top of a tall building and drop a ping pong ball and a rock, the rock is, you're not wrong, the rock is gonna hit the ground before the ping pong ball is. But what isn't so obvious to most people is that the only reason they fall at different speeds is because air resistance affects the motion of the ping pong ball more than it does the rock. And in fact, if there was no air resistance, every object that's not touching its surroundings would fall with an acceleration of 9.81 meters per second squared down. Okay? And I mean, you don't have any, like in your everyday life, you just don't have ways to get rid of air resistance. So like, how would you come up with that on your own and if you weren't just told that? And in fact, you know, some of the most famous, smartest scientists and philosophers in world history thought that gravity made heavier things fall faster than lighter things. It's just part of our kind of experience. The like great minds, the ancient Greeks, Aristotle and Plato and people like that, all thought that gravity made heavier things fall faster. But it turns out it's not gravity, it's just air resistance. So I'm going to show you a video that's, question?
Yeah.
Yeah.
I'm just like curious how they figured it out, that it wasn't gravity and that it was air.
Yeah, so they figured out by dropping two things that didn't vary a ton in the in how much air resistance affected their motion. Like, I mean, you could take a boulder and a small rock or something, and you could lift them up to the same height and drop them, and you could see that they landed at the same time, you know? So first, I mean, this was in the late 1600s, so a long time ago. People started kind of having this idea like, wait, it doesn't really seem to be it doesn't really seem to be weight that does this. And so they started to guess, like, okay, well, maybe if you got air resistance out of the equation, maybe everything would fall at the same rate. And then I don't know when the first time was that people made a vacuum to see what happened. There's a famous video, one of the things they did on the moon landing, the people up on the moon took a feather and a hammer and dropped them because there's no atmosphere on the moon, so there's no air resistance, and you can see them hit the ground at the same time, just from arms, from shoulder height or whatever. And it's a pretty grainy video, but you can make it out kind of. But so the video we're going to watch is a giant building that's used for aerospace applications, where they have the ability over, it takes a long time, many hours. They suck all the air out of this building, like huge high ceilings. And so now inside this room, there's no air at all. I mean, there's a small number of air molecules here and there or whatever, but not enough to affect the motion of anything. And so what we're going to see is, in really good, clear video, is they drop a bowling ball and a feather at the same time from, say, 20 feet high. First, they do it with the air in the room, and it happens exactly like you'd expect. The bowling ball smashes down to the ground. The feather slowly flutters down. But then they suck the air out of the room, do the same two things. They don't show it at full speed, which is, I think, a mistake, They show it in slow motion so you can see very clearly what's happening. But in slow motion, they show the two falling, and the feathers don't ripple in the least because there's no air to make them ripple, and they don't change position relative to each other. They fall exactly next to each other the whole way. When they hit the ground, the bowling ball smashes into the ground and breaks the thing it lands on. The feather hits the ground and bounces up violently like it was, made out of heavy rubber or whatever. And so it's just really cool to see. And so all I'm trying to do with this video and talking about it this way is ingrain in your head, like, your intuition is wrong about this, and you need to kind of go back and unlearn, however many years of intuition you've had about this. Okay, so let's watch it. What? Have they pulled the air out of this room yet or not? No, how can you tell?
He's walking.
Yes, he's alive, correct.
Oh yeah.
Yeah. Dang it, I keep hitting the wrong one. Okay. I don't want to overdo this, but do you know what would happen if instantly all the air disappeared from that room while he was in it? Long before he had a chance to suffocate because he can't breathe? The opposite. He would explode, and all of his blood, every liquid in his body, would instantly boil and expand, and it would happen so violently that there would be very little left to identify that was once a human form. And unfortunately, they know this from old professional commercial diving accidents that used to happen from time to time. There would only be like globs of gel. And so it's very, very gross. Okay, but we're not going to see that. They're going to wait till he gets out.
I heard that his saliva would boil because it's like an open system. But
yes.
Inside is it true that inside, since you have a closed system
Mm-hmm.
of blood circulation, is that also going to boil too immediately?
Yes, as the pressure, so you get a low pressure here, you have a high pressure here, so just everything wants to expand. And so everything's going to rupture instantly, and then everything's an open system. And it would all happen in a tiny fraction of a second, and it's very gross. If you want to learn more about people spontaneously combusting at low pressure, consult your local library. But there's, in like 1970 or something, there was this famous accident called the Byford Dolphin accident, catastrophe, whatever they call it. Yes.
Didn't he like, cause like it was like the pressure chamber and he didn't close the door?
Yes, that is exactly right. So in, okay, so like in so when people scuba dive, they go down, when you go down below the surface of the water, the pressure increases. And like at reasonable depths, people just equalize their ear pressure and that's all they have to worry about. But once you get down to a certain depth, there are all these major issues you have to deal with. One is that the nitrogen in your you take in so much more nitrogen into your blood that when you went back to the surface, that would boil and you can be killed from it if you've gone down deep enough. That's called the bends. Maybe you've heard of the bends. And so they're like, well, we need to be able to do construction on these super deep oil pipelines and stuff in the North Sea or wherever. And so what are we going to do? And you can overcome that if you come back to the surface very, very slowly and make stops along the way. Those are decompression stops. But if you're working at 200 meters below the surface of the water, it would take weeks or days at least for you to do all these decompression stops. So what are you going to do? Work for 6 hours and then stay days underwater coming back up? That's not going to work. So what they do is they put these people in a giant pressure vessel and they increase the pressure inside this container with the people inside until it's at the pressure that they're going to be working at 200 meters below sea level. And that they do that over a long time. And then the people, they send this pressure vessel down to where they're going to work. And the people just, without noticing any big difference, just kind of open the door and hop out and do their work for 8 hours, you know. Then they come back and they just live in this pressure vessel. And they could keep the pressure vessel down there at the bottom of the ocean where they're working. And they stay at this pressure for a month or something, you know. They could keep it down there, but it'd be really hard to get them food and stuff like that. So instead of leaving this thing down there, they just keep the pressure the same, and every time their shift is done, they pull it back up to the ship. And these people live at this super high pressure, but just on the ship. And if you want to pass them food or whatever, you have a double door system. You open one door. Well, I guess you open the door, pass the food in, then you shut that door, pressurize this section, then open this door, they get it. So it's all this double door system to keep the pressures, and the inside is this pressure just going back and forth between the two pressures. But yes, like you said, in this Byford Dolphin accident, somebody didn't completely shut one of those two doors. And so, you know, now they have like, this was kind of at the beginning of saturation diving. Now they have all these fail safes in place and these kind of things don't happen anymore. But someone didn't shut one of the doors, opened the other one, and instantly the pressure inside the pressure vessel went from 200 meters below the surface of the ocean to regular atmospheric pressure. And everybody was not only killed, they were like vaporized. I mean, literally just turned to vapor, you know? And so these saturation divers get paid a lot of money because it's very dangerous, but it's not as dangerous as it used to be.
That's why you go down a little bit at a time when you're diving and like release the pressure
Yeah,
and stuff. And
that's
then
right.
Wait for like 5 minutes.
That's right.
and then go-
That's right. But if you were gonna scuba dive to 200 meters,
Yeah.
it wouldn't take
I would
20 minutes or whatever. It would take
like a
days.
Yeah.
8 days to like decompress
Exactly.
and come
Yeah,
back
that
up.
was-
So you're like just there for
Yeah, freezing in the water in your wetsuit, so it just would never work. But yeah, saturation diving, it's crazy. Okay, what are we talking about? Physics? Okay, so no surprise there. Isn't that crazy? Okay, um, so if there's no air, any two objects fall with the exact same acceleration, and that acceleration is this. Okay, and in this class, when we do free fall and projectile motion problems, we're always going to assume that there's no air resistance. But we do have to think for a second about like, well, what is it that makes some things motion very strongly affected by air resistance and other things it's not very strongly affected? And there are three things. Oh, I'm getting ahead of myself. So I want to get this in your notes this way. There'll be a few things in this class, common misconceptions, where your intuition as you've grown up is kind of wrong about stuff. And I want to bring that out so that you, every time you think of it, you remind yourself like, no, it really works this way. Okay, so the first one is common misconception number 1. And this is, so it's often believed that gravity makes heavier things fall faster. Actually, what really happens is gravity makes all objects fall with an acceleration of 9.81 meters per second squared. When one object does fall faster than another, it's only because of air resistance. Okay? Okay, so the next question is, what are the factors that determine how much air resistance affects an object's motion? And there are 3 of these. So what determines the effect of air resistance on an object? Well, the first one, and this is why we all have, grow up with this false idea of what gravity does. The first one is motion is affected more for lighter objects, by air resistance. Motion is affected more by air resistance for lighter objects. And so if you have 2 objects that are the same size and shape, but they have different masses, air resistance is going to affect the lighter one more. And you can imagine like a pinball, like a metal pinball, and a ping pong ball that's basically the same shape and size. There's just a big difference in their weights. And if you drop those both off of the top of a building, the pinball is going to hit the ground a lot faster because it's less affected by gravity. The second factor is the surface area. So motion is affected more by air resistance for objects with a greater surface area. Well, there are some things that that are designed specifically to increase air resistance. Maybe the best example is a parachute. The way a parachute slows you down when you fall is it has a really big surface area catching the wind. And so if somebody, jumps from some height and somebody with a parachute with the same weight and everything jumps from the same height, the extra surface area of that parachute is going to make that person accelerate less. And then the last one, this is the one that matters the most. So this is the most important. Motion is affected more by air resistance for faster objects. Okay, so what that means is that how much an object is affected by air resistance, you can't really talk about it just in terms of the object. You have to know what kind of motion it's going through. So like, think about, okay, like how much is a baseball's motion affected by air resistance? Well, if you hold a baseball in your hand 2 feet above the table and drop it, it's barely affected at all. Like, we could assume there's no air resistance and our calculations would be perfect. But if you're talking about a baseball that's hit off a major league bat and leaves the bat at 110 miles per hour, then making that assumption would give you really bad approximations. One place you see this a lot is in, if anybody watches pro cycling, like the Tour de France kind of stuff. You notice that from day to day, they wear very different looking outfits. There are days where the outfits they wear are like rubber suits and streamlined helmets that tail off in the back, and it's like air resistance is everything on those days, like on time trials. And then there's other days where they go and they're just wearing regular shirts. They might even be wearing caps or something. It's like air resistance doesn't even exist. And so, like, what's the difference there? Well, the difference is on the days when they're going to be riding on their own at 35 miles an hour, air resistance is everything. On the days in the mountains where when they're by themselves, they're going to be riding at 15 miles an hour, air resistance is nothing. And so speed is a really important thing. Okay, we're almost there where we can do some problems. I want to give you two useful facts for using the constant acceleration equations for free fall and projectile motion. Okay, 2 useful facts for free fall and projectile motion. The first one is if an object is dropped, then its starting velocity is the same as what it's dropped from. Or maybe is the same as the velocity of what it's dropped from. So if you have an object and it doesn't matter what the object is, and you're driving in your car at 60 miles an hour and you let go of the object, right at the instant you let go of it, that object is moving 60 miles an hour, along the street. Yes?
It's the reason you don't want to just hop out of a moving car.
That's right. That's why it hurts to jump out of the car on the highway. Yeah. I learned that the hard way. And then on the other hand, if you drop an object from, well, we're going to do a problem where something's dropped from a bridge. Well, the bridge has a velocity of 0, so the object has a velocity of 0 right when you first let go of it. Okay, so we're going to use that all the time. The second important fact is if an object is launched upward, then when it reaches the highest point, at its highest point, its velocity is 0. So anytime you have a problem that mentions something that happens at the highest point, you're going to use the fact that at that instant the velocity is 0 every single time. Okay, so what you want to do is just store these two things in your head. Reaching the highest point in the flight means the velocity is 0 at that instant. And it's like the object, if you throw a ball into the air, it slows down, gets to a very slow speed, then it stops for an instant, and then its speed starts to increase in the other direction on the way down. Okay. So here it is, the first example of a free fall problem. So let's say that you're standing on top of a bridge and you want to know how high it is. But you don't have a tape measure long enough to reach the water. You could measure it like this. Okay, that's you. Take an object, a rock or something. Time how long it takes for the rock to hit the water with a stopwatch. And then you can do this calculation to estimate how high it is. Make sure there's no boats. So, okay, let's say that it takes 1.2 seconds for the rock to hit the water. How high is the bridge? And we're just going to go through the steps of the constant acceleration equations. The first step is to put your stickers down in the real world, what you're going to call zero position, what you're going to call the positive and negative directions. I always make the same choices for free fall and projectile motion problems. I find the lowest spot that's relevant to the problem. In this case, that would be the water, and I make that my zero. And then I always make the positive direction up. And you don't have to do that, but I do think it's helpful to always do things the same way on every problem. I think it helps you avoid dumb mistakes. So there's my zero and my positive direction. And then we have to choose when we're turning the stopwatch on and when we're turning the stopwatch off. What's going to be our time equals zero instant? Yep, it's the instant that it's released. And what's going to be the time final instant? When it hits the water. And I'm going to word this in a way that I think helps avoid a little confusion. We're going to do this problem as if the water isn't there at all. And we're just going to think of this rock reaching the water level. Okay? So, because I don't want you to think when the rock hits the water, its velocity suddenly stops. We don't want to think that way because, well, the constant acceleration equations aren't relevant once it touches something else. So I'm going to call this the instant it reaches the water level. So now we've made those four choices. Now we can figure out what variables we know and what variables we're trying to solve for. So here's the list. Okay, TF, do we know what the stopwatch says when we turn it off? Yep, we're given that that is equal to 1.2 seconds. Do we know the acceleration?
Yes.
We do. In free fall, we always know the acceleration. We know that it's 9.81 meters per second squared down. Is down positive or negative for us? Right. And so if you always choose your positive up, that acceleration is always negative. Do we know the position at time equals 0?
No.
No, that's what we're trying to figure out. Do we know the position when we turn off the stopwatch? Yes, that's where we chose our 0 position. So PF is equal to 0 meters. Do we know the velocity when at time equals 0? Yes, because of that thing. So it's being dropped from a bridge, which isn't moving. So that starting velocity is 0. So VI is equal to 0 meters per second. And then do we know V final? No, it's going to be some downward velocity. We could calculate that if we wanted, but for now we don't know it. But we're okay finding PI without it if we have to. Okay, and now we're going to go through the 3 constant acceleration equations and see if any of them work. We need something that has PI in it. So it's definitely not going to be the first equation, the VF equals VI. Yeah, I think the second one will work.
Because the other one has PF, or, sorry.
VF, that's right, yep. So the one that's going to work is PF is equal to PI plus VITF plus 1/2 A TF squared. And let's just go through and make sure it's going to work. So it does have PI in it. That's a good start. And then PF we know, VI we know, TF we know, and A we know. So yeah, this one's going to work. And now I'll just plug stuff in. 0 is equal to PI plus 0 times 1.2. 0 times anything is equal to 0, so that goes away. Plus 1/2 times negative 9.81 times 1.2 squared. And so 0 is equal to PI plus, well, this is going to be negative because of the negative sign there, negative 7.06. And so that initial height is 7.06 meters. So something like 22 feet if you're trying to visualize it. Any questions about that? Okay, let me do one more problem. And then in class next Monday, we'll just spend the class doing example problems and I'll let you work on it. We just want to sort of ingrain these techniques in your head. But for the second one, let's say a ball is thrown straight up into the air. From a height of 3 meters. And the initial speed when it's thrown or launched is 10 meters per second. What is the height of the ball at its highest point? Okay, so when you see anything about the highest point, you know that you're going to use the fact that when it reaches the highest point, the velocity is 0. Okay, so we're just basically waiting for our opportunity to use that fact. Okay. I guess I'll draw a little picture of what's going on. So let's say this height is 3 meters. And the ball is going to go up, reach its highest point, and then come straight back down. And we're trying to figure out what this height is at the highest point. like I said, the way I always tend to do it is I'll put my 0 position at the lowest relevant point in the problem, which is the ground. And I'll put my positive direction up, which means my negative direction is down. And now we have to choose the 2 instants for the stopwatch. In this case, the stopwatch is kind of like imaginary because it doesn't mention any times or anything. But still, we want to think like, what's the instant where we want to start timing, and what's the instant where we would want to know the time? And those instants are always based on when we have information and when we're trying to find information. Okay? So what's the earliest instant where we have information or want to find information?
3 meters.
Yeah, right at the start of the flight. So time equals 0 is going to be the instant it's thrown. Yeah, we know the height, and we're going to be able to figure out the velocity from the speed and direction and stuff. And then what do we want to call our time final?
My acceleration is 0.
When the velocity is 0. Yep, that's right. So this is going to be the instant that it reaches the highest point. And the way we're going to tell the math that is to say that the velocity is 0. So it's the instant it reaches the high point. And now we're going to figure out what variables we know and what variable we want. One, two, three, four, five, six. That's it. Okay. When we turn off the stopwatch, because the ball's at its highest point, do we know what the stopwatch says? No. Do we know the acceleration?
Yes.
Yes. That is always, no matter whether it's going up, going down, no matter what it's doing, that's always 9.81 meters per second squared down. So negative 9.8 to us. Do we know the position at time equals 0? Yes. If you go 3 meters from 0 in the positive direction, you're at positive 3. Do we know the position when it gets to the highest point?
No, we're trying to find out.
We're trying to find that. Do we know the velocity when it's thrown? We're given that. So that is plus or minus 10 meters per second.
It's going to be 12 volts.
Yes, and now you just think, is it moving, when it's first thrown, is it moving in the positive or negative direction? Up is positive, so this is positive 10. And then the last one, this is the one we've been waiting for. The final velocity, do we know what that is? 0, yep. And so now is there an equation that has PF in it and everything else in it is known? The one that's going to work, yep, is that third equation. One thing that you might notice is the third equation is the only one that doesn't have time final in it. So it's the only one that could work if you're trying to solve for something besides time final and you don't know time final. So this is the equation we want.
And will we get all these equations?
Yeah, I'll give you all any equations that you use, you'll be given on tests, and any conversion factors you need will be given.
So with like the formula for gravity, should we just memorize that one?
I think it would be hard not to memorize it, but it'll be on tests too. If you can learn to do this stuff without memorizing acceleration and gravity, that would be impressive. Okay, so now plug this stuff in. 2 times negative 9.81 times the quantity PF minus 3 is equal to 0 squared minus 10 squared. Remember that that negative is outside of the squared. Otherwise, the negative would go away, and that'll mess up your answers. So we have negative 19.62 times the quantity PF minus 3 is equal to negative 100. Divide both sides by negative 19.62, and you get PF minus 3 is equal to 5.08. Add 3 to both sides, and PF is equal to 8.08 meters. So it gets to a greatest height of somewhere around 25 feet after being thrown from about 10 feet. Anybody have any questions about that? We'll do some examples where you see this, but one thing to be careful about is if you're ever using these equations to solve for a variable that's squared and you have to take the square root of a variable, remember that the answer is plus or minus, and then you have to use the physical facts about the problem to determine, do I want the plus or the minus there? Okay. All right, that's it. See you on Monday and or in lab.